recording. So in this lecture, we will be talking about Lti systems and the Laplace transform, and we will go on to filter design and Butterworth filters as well. So let's take a look at the description of a Lti system in various forms. So the first form over here is to characterize the Lti system using its impulse response, small h of t. So things being characterized in the time domain using the impulse response. We saw this right at the beginning of this course. That's how we first characterize the Lti system, using the impulse response of that system. And how do you measure that? How do you determine that? Given input of impulse, delta of t, measure the output, h of t. So as soon as you do that, you've got its impulse response. And you can use that impulse response to perform convolution, to determine the output of that system for any new arbitrary input. You can do a lot of useful things with the impulse response. So that was one way to characterize this Lti system. So for this one, how did we use it? We said y of t, the output, is obtained by taking the input, and once you have the impulse response, you can convolve it with x of t to find the output. Also, just a quick note about the relationship between the impulse response and the step response. H of t, we derived earlier in the course that it is actually the derivative of the step response, dy step of t dt. So if you give it delta of t at the input, what you get at the output is called h of t, the impulse response. And for the step response, your input is u of t, your output in that particular case is y step of t. And these two guys are related by a differential equation. H of t is the derivative of y step of t. We proved this earlier on in the course. Okay, so that's one way to find the output of the Lti system. Take the input in time domain, take the impulse response in time domain, do the convolution in time domain, you get your response y of t, right? That's one way of doing it. And in some other cases, it might be useful to work in the Laplace domain or the frequency domain. Now, since we are talking about systems, we are going to be talking about transfer function. In the Fourier transform lectures, we were talking about frequency and frequency response, h of omega. Now we are talking about h of s because we are looking at the whole system as one transfer function. The only difference being we are not ignoring the real part of s, and we are talking about a more generalized Fourier transform, and we look at the region of convergence of h of s. As opposed to simply saying Fourier transform does not exist, we are going to make it exist over some region in the s plane. Let's see, with h of s, how do you find out y of s, or actually y of t? So for y of t here, actually I can first start with y of s. Y of s is simply the product of x of s multiplied by h of s. So if you know the transfer function of a particular system, h of s, find the Laplace transform of the input x of t, you get x of s, multiply them in the Laplace domain, get y of s, then take the inverse Laplace of y of s to get y of t, right? So it's a roundabout way of doing it. This is something similar to how we found the output using the Fourier transform, but it is an option for Lti systems. Multiply in the Laplace domain, then take the inverse Laplace transform, for which we will need the partial fraction expansion. So in the lectures that I recorded offline, all the cases of partial fraction expansions are detailed. Now, the third option over here to characterize the system is by explicitly mentioning how is the input related to the output for that system. So what is the relation? Can I write an equation that dictates the relationship between y of t and x of t? And usually for systems, for Lti systems, in continuous time domain, it's a differential equation. So it's an ordinary differential equation in continuous time domain, like t is continuous, or if you were thinking about discrete time, it would be a difference equation. right? A difference equation is, y of n equals x of n plus x of n plus 1. And that's the difference equation. And ordinary differential equation would have dy of dt equals x of t plus 5, right? Like that's a ordinary differential equation in the case of continuous time signal. But that's one way of doing it. So we've got three ways: impulse response, talk about the transfer function in the Laplace domain, or explicitly mention the relationship between input and output using a ordinary differential equation, which in the case of discrete time systems, it would be a difference equation. Now, let's take a look at characterizing LTI systems using the Laplace transform. So if suppose your input is x of t, your output is y of t, and the LTI system is being described in the third way using differential equations, how do I find the output y of t? For that, I would still need to go to h of s, right? The transfer function. So let's try to develop a generalized equation for h of s. That's what we are after. So let the input and output relationship of this general LTI system be described by a differential equation. Here we are considering a very, very generic differential equation here. You have the kth derivative of y of t with respect to time, and you are actually summing it up for k equals 0 to cap n. So on the left hand side of this equation, you have the first derivative, the zeroth derivative multiplied by a sub 0 plus a1 times the first derivative of y, a2 times the second derivative of y, a3 times the third derivative of y, plus and so on up to the nth derivative of y multiplied by a sub cap n, right? So that's a very, very generic way of writing that differential equation. On the left side, they are all output terms, y of t. And on the right side, we are combining all the input terms, x of t. So 0th derivative of x of t multiplied by b sub 0 plus first derivative of x of t with respect to t multiplied by b sub 1 plus and so on up to some cap m number of terms on the right side. So as you can see on the left and on the right, there are different number of terms. So very generic equation. With this differential equation, we can use the derivative property of Laplace, which says if you differentiate the signal in the time domain, you essentially multiply with s in the Laplace domain. So if you differentiate the signal n times, you essentially multiply the signal by s raised to n in the Laplace domain. So if we use this property along with the generalized differential equation for this system, we can get to the transfer function. Let's apply them. Using the above property for system ordinary differential equation below, we have, this is from earlier, just copy paste from before. Now we are trying to use the derivative property over here. ak, those are simply scalars, so they remain as is. The kth derivative of y is going to be s raised to k. S is the complex variable sigma plus j omega. S raised to k multiplied by the Laplace transform of y of t, the output, equals summation 0 to m. We are able to apply all of this because LTI system, right? Linearity applies. K equals 0 to m, b sub k remains as is, those are scalars, multiplied by s raised to k, again using the derivative property of Laplace, two-sided Laplace, s raised to k multiplied by x of s being the Laplace transform of small x of t. Once we have that, what we really need is the transfer function. So we need, let me highlight what we really need. We need y of s divided by x of s. That's what we need. That will be our h of s. So in order to find that, we are going to use these two conditions. One is, if x of t is delta of t, if we provide an input of impulse to this system, that would imply that the Laplace transform of an impulse is 1, right? That x of s is 1 in that case. So we would plug in x of s with a 1 there if y of s is being substituted by h of s. Because if input is delta, output will be impulse response. And if the output is impulse response, am I stuck here? Maybe I'm back. All right. So if the output is impulse response, y of s can be denoted by cap h of s. So instead of y of s, I'm going to substitute h of s here, and instead of x of s, I'm going to substitute a 1 over here. What do I get? H of s, which is independent of a, independent of k, comes out of that summation. K equals 0 to n, a sub k, s raised to k, that remains on the left hand side, equals another summation going for cap m plus 1 terms, b sub k, s raised to k, that remains on the right side. H of s, the transfer function of this system, Lti system, can now be represented as a ratio of polynomials. The numerator being a polynomial of order cap m, that's the highest power of s in the numerator, and the highest power of the denominator, oh my gosh, the highest power of the denominator, the highest power of s in the denominator is cap n. So the order of numerator polynomial is m, order of denominator polynomial is capital N. But it can be represented as a ratio of two polynomials. In our earlier lecture, we called it P of s divided by Q of s, right? That's the numerator polynomial, not delta s. And here you have things order cap m, and this is order small m, so, cap n, right? The highest power of s. So once you do that, what is left? We are going to use partial fractions, then we are going to find the inverse Laplace of h of s. That will give us the impulse response of this Lti system, right? In order to find the impulse response, we would need to evaluate inverse Laplace of h of s, which involves first breaking up into partial fractions. So what if we are after the step response, not the impulse response, the step response? How would we do that? We first recap the relationship or the connection between the impulse response h of t and the step response y step of t. We talked about this just a bit ago. The impulse response h of t of a Lti system is actually the first derivative of the step response y step of t. Now, if we take the Laplace transform on both sides, we have h of s on the left side equals s raised to 1 y step of s. So y step of s is the Laplace transform of y step of t. And we multiply s because we differentiate it in the time domain once. Y step of s consequently will be 1 over s h of s. So take the transfer function divided by s, as simple as that. You get the step response in the Laplace domain, y step of s. Now, another way of doing this would be to substitute x of t is u of t and y of t as y of s in the ordinary differential equation. So essentially that means that in your ordinary differential equation, you would put x of s as the Laplace transform of u of t, which is simply 1 over s. And for y of t, for y of s, you would substitute the Laplace transform of y step of t, which we are calling here as y step of s. So if you substituted these two conditions in the previous equation, let me just highlight that quickly here, right there. So y of s becomes y step of s, x of s becomes 1 over s, and then rearrange the terms, you can still get to that same result of y step of s is actually 1 over s multiplied by h of s. Transfer function divided by s, you get step response in Laplace domain. If you still need the step response in time domain, you still have that step of taking the inverse Laplace transform, for which again you may need partial fractions. All right, so let's do an example here. You are given h of s. So you're given the transfer function. Oh, actually, you need to find the transfer function, and you also need to find the impulse response for an LTI system. But what you're given is the input-output relationship using an ordinary differential equation. So once you have this ordinary differential equation, the moment I start seeing derivatives, I know that things are going to work out very well as soon as you go to the Laplace domain. So the first step I would do, let me draw a line here. So the first step I would do is take the Laplace transform on both sides. So the second derivative of y is going to become s squared y of s, and 5 times first derivative of y is going to become 5y of s. Now, there are some horror stories about 5 and s written in the same equation, because it is, as you are working through multiple steps, it can be a pain to differentiate between 5 and s. Yes. So make sure that you clearly write 5 and s. I have seen several students struggle with that, because as you are going through multiple steps, it's easy to lose track of which one is 5 and which one is s. Can we write s in cursive? I will try my best. So are we talking about this? Sure, let's do that. All right, so I've got s squared y of s plus 5y of s, let's see, plus 6 y of t would become, oh, hold on, 5 first derivative. There should be an s there as well. Let's move this a little bit. 5s y of s plus 6 y of s. And on the right side, what do we have? S x of s plus x of t becomes x of s. So that's taking Laplace transform on both sides. Now things are going to be very simple, because now you're going to combine the y of s terms and combine the x of s terms, divide things to complete h of s. So let's quickly do this. Y of s, if I take that as a common factor here, I'm going to be left with s squared plus 5s plus 6 on the left side, and on the right side I will have cap x of s multiplied with s plus 1, and my h of s, the transfer function, is going to be y divided by x, which is going to be what? S plus 1 divided by s squared plus 5s plus 6. All right, we have got a proper fraction here. We don't need to do any polynomial division. We've got a proper fraction. The order of the numerator is 1 less than the order of the denominator polynomial. That's good. We can straight away move into partial fractions. But for that, first we need to factor the denominator. So let me write those steps here. I have done that to save time already. You've got s plus 2 and s plus 3. Those are the factors of the denominator, which can be written using partial fractions as some k1 divided by s plus 2 plus k2 divided by s plus 3. And when you evaluate k1 and k2 using partial fraction tricks, you get -1 divided by s plus 2 and 2 divided by s plus 3. So that would be your h of s. That's your first goal. Now h of t, which is inverse Laplace of h of s, is going to equal For negative 1 over s plus 2, you have negative 1 multiplied by e raised to negative 2t u of t plus 2 e minus 3t u of t. So by simply using the Laplace transform pair for 1 over s plus a, we have written the impulse response here. So we did this guy as well. All right, questions about this example? Very straightforward. You are given the differential equation, take Laplace transform, combine terms, divide to get the transfer function, use partial, so factor the denominator polynomial, use partial fractions, take the inverse Laplace transform. All right, so all those steps I believe for you guys are kind of straightforward. With that, let us move on to talk about the pole zero plot. Some of this should be a repetition. Assume that the Laplace transform h of s can be written as a ratio of polynomials using the complex variable s. So in s, it is a rational Laplace transform, a ratio of two polynomials. H of s written as p of s divided by q of s. Polynomial in the numerator divided by the polynomial in the denominator, which is called the transfer function of this system, of a system. P of s, which is the numerator polynomial, if you find the roots of p of s or the values of s for which the numerator goes to 0, those are called zeros of the system. That's when the system goes to a 0. H of s is going to go to 0 at that point. Q of s, which is the denominator polynomial, the roots of q of s are called the poles of the system. So those are values of s for which h of s goes to infinity. Now, with those zeros and poles comes in a lot of insight about how the system behaves. So let's start with the pole zero plot. A pole zero plot is a plot of s-plane where your x-axis is sigma, the real part of s, and the y-axis is j omega, j multiplied by the imaginary part of s. So things that are real go on the real axis, things that are imaginary go on the purely imaginary go on the y-axis, and things that are complex can go anywhere in the first, second, third, fourth quadrant. Over here, what we are dealing with is an example with two zeros at 1. Right, those are the values of 1. Those are the values of s for which x of s goes to 0. But there are two of them at the same point. Those are indicated by drawing two circles at 1 on the real axis because those are real zeros. Zeros don't affect that much, but the location of the poles actually determines everything about system stability. So the two poles over here are at -1. Let me highlight them in colors. -1 is that guy, and at 2 is that guy. So that's 2 and that's 1. So they are also real poles. However, one is on the left side and one is on the right side. You know what? I should have probably highlighted this with green and highlighted this with red. The reason being, or pink. The reason being, poles, if they lie on the left side of the S-plane, they actually lead to stable behavior. When the poles are in the right half of the S-plane, that is actually an unstable system behavior. We will see that in a minute. All right, so that's your pole zero plot, which gives you an insight about system stability. Now let's come to the most important slide of today, the location of poles. If you know where the poles lie, you know about the stability behavior of a system, whether you are going to have a stable system or an unstable system, or maybe a marginally stable system. So let's talk about why location of the poles matters so much. So start with our statement here. The poles are important because when we calculate the impulse response h of t from h of s, we can use partial fraction expansion to write h of s using many terms, but they're all, each term can be uh, the inverse Laplace transform of each term can be evaluated, because now it is in the form of 1 divided by s plus a, right, or 1 divided by s minus a, one of the common terms for which you get a complex sorry, not complex, e to the p1t u of t, right. For each term you can look up the inverse Laplace. So first we use partial fraction on h of s to write h of s in this form in multiple terms. Then we find the inverse Laplace of h of s, which will give us the impulse response h of t. And because we were able to do this partial fraction expansion and write it in this form, we know that h of t is going to be a linear combination. a1, a2, a3 and so on are just scalars. So it's going to be a1 multiplied by e to the p1t u of t, and a2 e to the p2t u of t, and so on, right? So it's going to be a linear combination of e to the p1t, e to the p2t, and so on up to e to the pnt. Now, once we have that result, let's take a look at generally a pole P can be a complex number. So if we can write P as some sigma plus j omega, some constant here, then e raised to pt can be written as e raised to sigma plus j omega t. And you can isolate the real and imaginary part into two separate exponentials that are getting multiplied, e raised to sigma t, e raised to j omega t. And if you take the magnitude on both sides, the magnitude of e to the pt is actually simply e to the sigma t, because e to the j omega t doesn't contribute to the magnitude, it only contributes to the phase. Magnitude of e to the j omega t is 1. So e to the sigma t, focus on this. When sigma is negative, e to the negative 5t, e to the negative 10t, e to the negative 100t, this will be a decaying exponential. If you have a decaying exponential as time increases, you have stable behavior because things are decaying with time, right? Things are settling down, things are decreasing with time, things are, getting smaller and smaller as time grows. That is stable behavior. But on the other hand, when sigma is positive, what is going to happen? As time increases, e to the sigma t actually grows exponentially. That is unstable behavior. That is a growing exponential. So with that information, we can write these two statements. With sigma being negative, as time increases, goes to infinity, absolute of e to the pt actually tends to 0, which means it is going towards stable behavior. What is a stable behavior? Think of a pendulum that is hanging from the ceiling, right? As time goes to infinity, what happens? If you don't give it any new input, any new movement, any new force, what is going to happen? The pendulum is going to settle down and the output is going to eventually become 0 because it's going to stop moving. That is stable behavior. But you can have an unstable behavior as time goes to infinity. Now, for unstable behavior, think about the feedback that you get. Imagine a speaker using a microphone with a large gain. You guys must have noticed that if the gain is large and you're using a speaker system with a microphone, what happens is, because of feedback, you will get a very, very uncomfortable noise which grows with time. So that indicates that the absolute of e to the pt is actually growing, is tending to infinity as time goes to infinity. And that happens when sigma is greater than 0, for time greater than 0, right? Both these statements combined give us this very important result that is written on the right here, bottom right here. Due to this, when we design systems, you want the real part of the poles to be negative, meaning you want the poles to be in the left half of the S-plane. If the poles of the system are in the left half of the system, that means the system is asymptotically stable. asymptotically because t goes to infinity, right? So as time goes on, it asymptotically becomes stable. So when poles are negative real parts, so that means if they are on the left side of this plane, right? All of this is green. Over here, all of this is green. I just need to be away from the j omega axis. On the j omega axis, something else happens. We'll talk about that. But I know for sure that if you go to the right side, you are in danger. You want to avoid poles on the right half of the plane. So that's asymptotically stable behavior. So that's good. You want to be in the negative half of the S plane. Now let's talk about is the location of zeros. No, not at all. With respect to stability, the location of the zeros is not at all relevant. It's the poles that dictate unstable behavior, because things becoming zero, they are finite. They belong to the region of convergence. That's good. Like it's not unstable behavior. Zeros play a role in different things. The different things being, how is the response of the system going to be? That is dictated by where the zeros are in terms of the shape of the response, not as much as the stability of the system, right? So stability only depends on the poles, location of the poles. So over here, let's do a quick exercise of sketching an arbitrary impulse response. So all of these are time, and I'm going to associate a stable or unstable behavior for each h of t impulse response. And I'm going to assume that all of these are causal. So causal, what does that mean? Causal means that the h of t is h of t implies h of t is 0 for time less than 0, right? So there's no impulse response for negative time. So I'm assuming causal systems, and I'm trying to sketch a impulse response of 3 different types of systems, and I'm going to go through a system stability classification. So if your impulse response looks something like this, as you give it energy at the input, your output becomes energy, and then it kind of goes to 0, right? That's one possibility. You got the energy at the input, but that energy kind of went away with time. The other possibility is, as soon as you gave it energy at the input, you had something that did something like that. It started growing with time. That's the other possibility. And your last possibility over here is, am I stuck again? Okay. My last possibility is something in the middle of these two, which is what? The oscillations keep going on forever. So if the system impulse response looks like the one at the top, that is actually asymptotically stable system. The next one, obviously, it is growing with time, so that's unstable, right? So it's asymptotically unstable. Impulse response is growing with time. The last one is called marginally stable. It is like balancing something on your finger, right? It's stable, but you have to work a lot to keep it stable. It is marginally stable. Whenever I think about marginally stable, I think about the last scene of the movie Inception. Anybody remember that? The tabletop spinning. Oh yeah. Whenever I think about marginally stable, I think about that, right? It keeps going, but it is on the edge. It might be stable, it might be not stable, but it is just managing to be stable. That's marginally stable behavior. All right, so let's classify them a little bit more in detail. So you've got this LTI system. In time, you have X and H and Y, input, impulse response, output. In the Laplace domain, you have cap X of S, H of S, Y of S. Laplace transform of X of T, transfer function, Laplace transform of Y of T, right? Those are the, am I stuck again? Oh my gosh. All right, so that's your general view of an LTI system here. We are considering causal systems, which means that all right, Jacob, I will answer your question sometime later. Yeah, yes, I think they're still in the dream world, but the explanation for that I will give you later. All right, let's talk about some definitions of asymptotically stable, unstable, marginally stable. How do I classify that, and how does that relate to the location of the poles? So the first one is asymptotically stable. That means that if I take away my input, if I I should probably use green for this slide because it's stable, it's good, it's green. If I take away the input, if I make X of T 0, then output eventually becomes 0. Asymptotically, output becomes 0 if I remove the input. So if I don't give it any input, if I don't give it any energy, the response of that system will die out as time goes on. That's asymptotically stable behavior. For this, we already established that the poles need to lie in the left half plane. How does that look like? Well, if I sketch the poles, one possibility is poles are here. The other possibility is poles are here. Poles always appear as complex conjugates of each other. So you will have those. Or poles might be, here and here, two of them at the same point. But if you have poles on the left side, completely on the left side, excluding the j omega axis. So on j omega axis is not stable. It's actually marginally stable if you're there. So if you are on the left half plane, what does that mean? That means that the roots of the denominator polynomial have negative real parts. Sigma is negative, right? So all of that is green. Exclude y-axis. Let's move on to the next one. Asymptotically marginally stable, right? As time goes to infinity. So let me use some color between green and red. Let me use blue here, yellow here. If you take away the input x of t 0, then as time goes on to infinity, y of t doesn't become 0, doesn't become infinity. It actually becomes a bounded value. The way we have shown earlier with oscillations, right? Oscillations keep going on at the last case here. So that's asymptotically marginally stable behavior. Bounded value for y of t. So here an LTI system is asymptotically marginally stable if and only if there are no roots of q of s in the right half plane, no poles in the right half plane. That's one condition. And there should be no repeated roots on the j omega axis. So you cannot have repeated roots on the j omega axis, and you cannot have any poles on the right half plane. If those conditions are met, then you have marginally stable behavior. How would that look like? Well, that would simply look like this. If you have, suppose, poles 1 and 2, right? You have two poles here. They are not repeated, but there are two unique poles on the j omega axis. That will lead to marginally stable behavior. Next, we have asymptotically unstable behavior. What is that? if you make the input 0, your output becomes infinity, grows out of bounds as time grows. So as time increases, your output becomes unbounded, and that is unstable behavior. Something that we indicated by an exponential growth earlier. So an LTI system with asymptotically unstable if and only if there are at least one root in the right half plane, right? Even if you have one root in the right half plane, it is unstable right away. Or if you have repeated roots of q of s on the j omega axis. So if you have repeated roots on the j omega axis, that's actually not marginally stable behavior, that's actually unstable behavior. Or worse, if you have a pole on the right half plane, at least one pole in the right half plane, right away you have unstable behavior for causal LTI systems. Now coming to bounded input, bounded output stable behavior. So far we have been talking about input is 0, what happens to the output, right? So when you take away the input, what happens to the output? What about if there is a bounded input, will the output be bounded or not, right? So is the system bounded input, bounded output stable or not? And we can establish a relationship between asymptotic behavior, stable behavior, and bounded input, bounded output stable behavior. For those three conditions, if the system is asymptotically stable, then it is bounded input, bounded output stable. If the system is marginally or unstable, then the system is bounded input, bounded output unstable. So we are not proving this here, we are just recognizing the relationship between asymptotic behavior and a bounded input, bounded output behavior. And this is different from before because this is bounded input. So there could be a bound on x of t, some bx. Over here, in the earlier three cases, we made the input 0 and then observed the output as time increases. So the slight difference between the two. All right, let's move on to unilateral Laplace transform. And the reason why we need to talk about unilateral Laplace transform is because our system h of s, or characterized by h of t, could have some initial conditions. So for example, whenever I think about initial conditions, right away I think about a capacitor, right? So when you are using a capacitor, a lot of times you assume that the initial charge stored in a capacitor is 0. But it is very possible for you to have some initial charge in the capacitor, and then you will use that in order to find your response of that capacitor, right? Like you will need that initial charge information to go on further with the circuit analysis of that capacitor. So unilateral Laplace transform comes into the picture where systems have an initial state, some initial value, non-zero initial state, right? So a one-sided Laplace transform starting at time just before 0 minus. What is that? F of s is defined as integration from 0 minus to infinity, one-sided, f of t e to the minus st dt. Very similar to the Laplace definition before, except that the lower bound is now at just before 0. It is only one-sided, positive time, but it starts just before 0 time. That's a one-sided Laplace transform. Earlier we were talking about a two-sided Laplace transform, and we were ignoring the initial state there. Both the transforms, bilateral, the one we looked before, and unilateral, share almost all the properties. So the multiplication property, the frequency shift property, so a lot of the properties are shared between bilateral and unilateral transforms. However, there is one significant difference in the time differentiation property. Highlight that. Time differentiation property for bilateral and unilateral transforms are very different. So for bilateral transform, as soon as you differentiate in time domain, you multiply by an s in the Laplace domain. The more you differentiate in time, the more you keep multiplying by increasing powers of s in the Laplace domain. However, when you do this for a unilateral Laplace transform, every time you differentiate, you not only increase the power of s, but you also include the initial state and the derivative of the initial state evaluated at 0 minus. at the time 0, just before 0. So we need to also include those terms with this. Let me highlight them in a different color because they are different from this. Initial state evaluated at time just before 0. Initial state initial state evaluated at time before 0 multiplied by s, and also the first derivative of the function in time domain evaluated at 0 minus is also present in this equation. And then this keeps growing. This list keeps going down. So in general, for unilateral Laplace transform, the nth derivative in the time domain of the function f of t in the Laplace domain, that would be s raised to n multiplied by f of s, but you will have other terms that depend on the initial state. So for example, you will have s raised to s minus n minus 1 multiplied by signal evaluated at time 0 minus, first derivative of f of t evaluated at 0 minus, second derivative of f of t evaluated at 0 minus, and so on. So all these conditions over here, essentially you will need that, right? So initial conditions need to be provided. Need to be given. So once you have that, then you can substitute in this to evaluate the Laplace equation. Let's take a look at an example. Before that, a little bit of background. So most linear time invariant systems can be modeled using ordinary differential equations. We have seen that already. But the systems with no initial conditions, we evaluate their bilateral Laplace transform of the ordinary differential equations. We have seen an example of that. But with systems with initial conditions, we need to evaluate the unilateral Laplace transforms for the ordinary differential equations. So the response of Lti systems in the general case where there are initial conditions is a combination, is an addition of two separate responses, y sub zi of t plus y sub zs of t. Z sub I stands for zero input. So this is the response due to initial conditions, right? Only due to the initial conditions, what is the response? That's y sub zi of t. And we need to add the response due to the input, initial conditions plus the new input. So a response due to the initial input is called zero initial state. So what would be the response of this system if there was no initial state? That is response due to the input, right? So we are calling that as y sub zs of t. So both those responses add up to give you the overall response of the Lti system, for which we need the unilateral Laplace transform. So let's take a look at an example here. We are asked to find the response y of t given an Lti system ordinary differential equation, and we are also given initial conditions. So we have second derivative of y plus 5 times the first derivative of y of t plus 6 times y of t equals the first derivative of x, the input, plus x of t. We are given that the initial condition for output just before 0 time is 2. The first derivative of y evaluated at 0 minus is 1. And the input is e raised to minus 4t u of t. So given all of that, how do you find y of t? The overall response, which can actually be separated into two responses. One is due to zero initial state, one is due to zero input. So let's start with taking the Laplace transform of both sides. If you take the Laplace transform of both sides, what do you have? You have for second derivative of 5, you have s squared y of s minus s y of 0 minus y prime of 0 minus. So I've color coded this so that you guys can follow along which term corresponds to what. And in blue, you have 5 times dy by dt. So 5 times s y of s minus y of 0 minus. 6y of t becomes 6y of s. On the right side, dx by dt becomes s x of s minus x of 0 minus, plus x of t becomes x of s. Now, once we have here this step, we are going to substitute the initial conditions. So, for example, let's see, this guy becomes a 2, and then let's see, y sub minus, okay, so this guy becomes a 1, and let's see, this guy is also a 2, right? Yes. What else? I think we can also evaluate this, right? X of 0 minus, what is it going to be? E raised to minus 4t u of t. What is that? Just before time 0, u of t is 0. So that will give you 0 there. Substitute the initial conditions, plug and play, combine the y of s terms on the left side, combine the terms on the right side with x of s. Find the Laplace transform of x of t. E raised to minus 4t u of t is 1 divided by s plus 4. So plug that in here. And write y of s as two separate terms. One is s plus 1. So s plus 1 came in from here. Color coding. All right, green. S plus 1 divided by all of that. That's one term. So that's that guy right there. And then the next one is going to be s plus 1 again. 2s minus 11. So goes to the right side, it becomes 2s plus 11 divided by the same y of s coefficient. So that's going to be that. And as you can see, the 2s minus 11 is coming due to the initial conditions, y of 0 minus, y prime of 0 minus, and y of 0 minus, and x of 0 minus. So that 2s minus 11 term is because of all of that, which means that is going to relate to y cap y sub zi, 0 input of s. Once we have that, we go through the cycles, do the partial fractions, separate them out into multiple terms, individually find the inverse Laplace transform. And because we have done that separation, we were able to isolate the response due to zero state and 0 input, 0 initial state and 0 input. So that would be your complete response, the addition of those two. All right, so that's an example that we just went through. Questions about this example? Take the ordinary differential equation, evaluate the unilateral Laplace transform, plug in the input conditions, they have to be given, combine the terms, manipulate the expressions to write y of s, use factor the denominator, use partial fractions, then do the inverse Laplace. So lots of steps, but I hope there's nothing over here that is too difficult to do. Just math. No questions. Move on. Let's see. For an LTI system to be causal and stable, what do I need to look for if the LTI system is causal and stable? If it is causal and stable, causal means that the impulse response is only defined for positive time. Stable means that the response will become 0 eventually if you remove the input. If you don't provide any energy, eventually asymptotically it will go to a 0 output. If Those two conditions have to be met, causality and stability. Then you need to have all the poles of h of s, the transfer function, in the left half plane. All the poles have to be in the left half plane, excluding the j omega axis, because if you are on the j omega axis, you are either marginally stable or you are unstable if you have repeated roots there. So you have to be in the left half plane. The second one is the region of convergence has to be right-sided and it should contain the j omega axis. Why is that? Because we have said causal behavior. For causal signals, you have an impulse response that starts at 0 and moves right. So it's a right-sided signal for the impulse response, which means our region of convergence is going to be right-sided. But because we have poles in the left half plane, the region of convergence is going to contain the j omega axis. So for example, if I quickly draw this out, suppose I have two poles. Let me make the poles complex conjugates of each other. So if you have two poles on the left hand side, it's good. Let me also mark these guys, right? This is sigma, this is j omega axis. If I have two poles, complex conjugates of each other, I know that I've met the first condition, so it's stable behavior. Where is the region of convergence for this? The region of convergence is going to be to the right. So if I can draw an imaginary vertical line here, a dotted red line, my region of convergence I'm going to highlight in green here, and that's going to be my ROC in green. So it will contain the j omega axis clearly. The only condition is poles cannot be on the j omega axis. That will lead to marginally stable behavior. Okay, let's move on to a slightly different topic here with filter design. So what is coming your way is the design of Butterworth filters using the Laplace transform techniques that we have seen. Where should I put the poles of the system in order to get a particular type of filter? That's where we are going with this. And the type of filter that we are designing is a Butterworth filter, which has two essential properties. One is in the pass band, the response has to be really, really flat. And in the stop band, eventually the frequency response should go to 0 as frequency omega increases. That's a Butterworth low pass filter objective. More about that in just a bit. And we'll also take a look at some filter transformations, meaning if I start designing a low pass filter, can I transform that low pass filter to a band pass filter? So how can I do that using the Laplace techniques that we have seen? We'll begin with identifying 4 ideal filters. The filters are low pass filter LPF, high pass filter HPF, band pass filter BPF, and a band stop filter BSF. Each of the filters are recognized by their frequency responses. So notice now for h of j omega or h of omega, we are calling that the frequency response of the filter. H of s, that's our transfer function. So two different things. One is giving you system behavior, one is giving you behavior with respect to omega. One is giving you behavior with respect to both sigma and j omega, horizontal and vertical axis. Frequency response only gives you the information about the vertical axis of the S-plane, which is omega. That's it. So for a low pass filter, these are all ideal filters, ideal brick wall filters. Let's take a look at their frequency responses individually. H of omega with respect to omega, low pass filter. So it is going to pass frequencies that are between 0 and some cutoff frequency omega sub c, cutoff radian frequency. So how is it defined? H of 0 is 1 and H of infinity is 0. So it starts off with a 1 at the pass band, and in the stop band it eventually becomes a 0. And because these are ideal filters, we are drawing them as sharp rectangles. These are also called as brick wall filters. Let's move on to 2. High pass filter, exactly the opposite of low pass filter. So beyond a cutoff frequency, it will start passing those frequencies. So h of 0 is 1, h of infinity is 1. H of 0 is 0, over here it is 0, h of infinity, as frequency increases, it goes to a 1. Again, ideal behavior, ideal frequency response of a high pass filter. These are all frequency responses. J omega, or you can call that h of omega, either one. Next, ideal band pass filter. You have the frequency axis as x, h of omega, your frequency response on the y-axis. So between omega 1 and omega 2, things pass, but outside of that band, things will not pass. So it's only going to pass this band of frequencies between omega 1 and omega 2. So h of 0 is 0. And h of infinity is also 0. But it is 1 green between omega 1 and omega 2. So bandwidth of this bandpass filter is simply the omega 2 minus omega 1 here. What is the bandwidth here? Bandwidth over here is omega c, right? Let's do this. 4. Band stop filter, opposite of band pass filter. What do we have here? We have an ideal filter that stops frequencies between omega 1 and omega 2. So let me highlight them. At 0 it is 1, at infinity it is 1, but between omega 1 and omega 2 it is 0. So it is stopping the band of frequencies between omega 1 and omega 2. So 4 ideal filter frequency responses and their the evaluation of that frequency response at low frequencies, extremely low frequencies and extremely high frequencies. H of 0, h of infinity, cap h of 0 and cap h of infinity. Next, there is also another type of filter which passes all frequencies, all pass filter. So if you have an all pass filter, it has no change in behavior with respect to frequency. So it's essentially saying I will pass all the frequencies to the that are present in the signal that's coming in, right? So the magnitude of h of omega at the all pass filter is 1 for all omega, or you can actually call this 1 or some constant, right? Doesn't matter. It is passing all frequencies, so it may have some gain as well. That's fine. An example of a all pass filter is a delay filter. So something that gets delayed by cap t. So if you have an input here, let's suppose you have an input some x of t, right? And the output is x of t minus cap t. So that's a delay filter, right? So that is doing nothing, but in frequency, it would be a multiplication of e to the minus j omega t, cap t, right? Where cap t is the delay, amount of delay. So that is an all pass filter. It's actually a delay element. So that's another type of filter that you can think of. Not very useful because it's not doing some selectivity with respect to frequencies. It's just passing all the frequencies. Now, an important question here is, why are, before we talk about Butterworth, we need to address this. Why are ideal filters not practical? And the reason for that is, if you look at the frequency response, omega, for a low pass filter, if you look at h of omega, what was it? It was a brick wall filter, right? A rectangle between some omega c and minus omega c, some gain 1. What does that mean in terms of its impulse response? If you take the inverse Fourier transform of this to go from h of omega back to h of t, we would need to take the inverse Laplace of that. If you take the inverse Laplace of that, what shape do you get in time? Anyone? Sync is right, absolutely. you get a sink in the time domain. What does that mean? Non-causal, absolutely. Non-causal behavior, which is why it is not practical. So 0 is here. You have things on the positive time as well as on the negative time. That means it is not causal, which means it is not practical. In fact, what people do is they chop off. So if you have to design it with this technique, you can actually just chop off the sink and shift it right. And by doing that, you will get sort of a low pass filter, but it will not be an ideal filter. It will have some roll off, some transition band, and there will also be some ripple in the pass band as well as in the stop band. But it is possible to do that if you are able to truncate h of t to some finite value and then shift it to the right by half of that value. Right? So force it to become causal, but still preserve that shape. So there will be some phase repercussions, but at least the magnitude of the frequency response will be very much like a low pass filter. Now let's come to the practical filters. So we answered the question, what is not practical about ideal filters, which leads us into Butterworth filters, which are more practical filters. So we need to work with some approximations, right? So practical filters are derived from various approximations to an ideal brick wall filter. What do you have with the ideal brick wall filter? We have two things. One is, so if you think about this, the ideal characteristics of this filter are, in the pass band, the frequency response is constant. It's a 1. It's a maximally flat response in the pass band. That's one aspect of this. The other aspect is, as omega increases to infinity, h of omega goes to 0. So that's the other aspect. So those two, considering those two things, we can approximate an ideal brick wall filter and make it into a practical filter. In this case, we are calling that particular one with those two approximations as a Butterworth filter. Now, depending on how sharp you need that roll-off to be, the order of that Butterworth filter might be too high or too low, right? So it might be a third order filter, or it might be a 10th order filter, depending on how slow or how fast you need to transition. So if you want to transition like an ideal filter very sharply in frequency, then you will need a higher order filter for that. So let's take a look at some approximations that we would need to do this. The first one is the Taylor series expansion. So I can express any function f of x, and I can do a Taylor series expansion at x equals 0. And I can actually do that at x equals 1 at a different value as well. But here I'm writing the Taylor series approximation for a function f of x using the values at x equals 0. How can I do that? I can do that by simply writing f of x equals f of 0, evaluate the function at 0, plus the first derivative of f with respect to x evaluated at 0 times x, plus 1 over 2 factorial and so on. So this is simply a power series equation, right? So at a particular time 0, anybody has a question? All right, let's continue. So at any time or any x 0, I can approximate the function by using the Taylor series expansion as we have written over here. For this, what would I need? I would need to evaluate the function at 0. I would need to evaluate its continuous derivatives, so f prime, f double prime, and so on, and multiply each of those derivatives with that x or x squared and so on, right? So if I do that, the first derivative multiplied by x, that gives me the linear part in that function. This gives me the quadratic part in the function, and then that gives me a cubic part of the equation and so on. So essentially I'm saying I can represent f of x as a polynomial in x at any value of x. Right here I'm using x equals 0. So I'm going to need this to derive this Butterworth filter. So let's take a look at some filter specifications. This is a low pass filter, very practical looking low pass filter, because it has a ripple in the pass band, it has a ripple in the stop band, and it has a transition. It is not going down to 0 immediately, right? So pass band indicated in green because those frequencies are passing through. So any frequency, any radiant frequency between 0 and omega sub p are going through this filter. There is a transition band between omega sub p and omega sub s. Notice the color here transitioning from green to red. And as you go into the stop band, what order of filter is this? Oh, I don't know yet. It looks like a very, very low order filter because things are, slow in transition. There's a lot of ripple that is shown. This is just an arbitrary filter spec. Now let's take a look at some other ones. So stop band beyond omega sub s. There is also some ripple in the pass band and there is some ripple in the stop band. What is the amount of ripple in the pass band? If this midpoint is 1, it can go up as high as 1 plus delta sub 1 and it can go as low as 1 minus delta sub 1. So delta 1 is actually called the pass band ripple and delta 2 is called the stop band ripple. Ideally, you would want 0 pass band ripple, 0 stop band ripple and 0 transition band, or at least as small as possible. Note over here, we are only showing the positive frequencies. The image of this is also present, which we are not showing here, right? So we are only showing positive here. There's also a flipped version present for negative frequencies, which is not being shown in this plot. Pass band between negative omega sub p and omega sub p. Stop band beyond omega sub s and beyond negative omega sub s on the other side. Transition band between omega p and omega s. And you would want transition band as small as possible, ripple and stop band ripple, both ripples to be as small as possible as well. That's how you go to an ideal filter. So let's start our discussion of Butterworth filters with a third order filter. And the moment you see third order filter, you know that the transfer function of this filter is going to have a cubic equation in the denominator polynomial. So right away you notice b of s, some transfer function of this filter, has a cubic in the denominator, s cubed. That's how you know it's a third order filter. Now, we are sketching multiple things here. One is the ideal brick wall filter in black. Cutoff frequency omega sub c. That's the ideal behavior. But we don't have ideal behavior. We have to physically realize this using a rational transfer function. So we are going for a b of j omega, some other filter whose frequency response we are calling that as cap b and shown in green. So some transition band, some pass band, and then stop band here, right? Again, we are doing this for a low pass filter. In general, I can write b of s as some constant plus a1s divided by another polynomial here, right? b sub 0 plus b1s plus b2s squared plus b3s cubed. This is a general third order filter transfer function. Now, if I was able to find all the coefficients a0, a1, a1, b0, b1, b2, b3, if I was able to find that, then I know what that physically realizable rational transfer function is. So my goal will be to determine these coefficients a0, a1, b0, b1, b2, b3 such that I achieve two conditions. One is maximally flat behavior. What does that mean? That means that I want this to be as flat as possible. The green guy should be closer to the black guy in the pass band. It should be as flat as possible in the pass band, right? Right now I'm discriminating against the higher frequencies here. I don't want that. I want to be fair to all frequencies in the pass band. This is the pass band. So I want to be fair to all those frequencies. But if I go with the green one, I'm not being fair. I will become fair to all frequencies if I had a maximally flat response in the pass band. So that's one. The other condition is that as omega goes to 0, as omega goes to infinity, I should go smoothly to 0, right? That's the other condition. As omega increases, as frequency increases, go to 0 eventually. That's that. So be flat in the pass band and go to 0 as omega increases. So those are the two conditions I'm going to use in order to determine the coefficients A0, A1, B0, B1, B2, B3. So there's going to be a lot of math coming your way. I'm going to walk you through it, but the objective here is to follow along. I'm not going to expect you to kind of apply this on an exam. Maybe a homework, but not on an exam. The results of the derivation, though, that you can use in interesting ways, but the derivation is just meant for you to follow and maybe do a simpler exercise in the homework, but not on the exam. So let's try to use the Taylor series expansion of B of j omega. So instead of B of S, the transfer function, I'm using the frequency response of this filter, B of j omega, the magnitude of that, and I'm doing the Taylor series expansion at omega equals 0. I want this to be maximally flat at low frequencies because this filter is a low pass filter. So if I use Taylor series, I can write, earlier we used f of x, now instead of f of x, we have absolute of B of j omega. B of j omega can be written as absolute of B of j omega at omega equals 0, plus the first derivative evaluated at omega equals 0, and the derivatives are with respect to omega, multiplied by omega, so that's the linear term there. 1 divided by 2 factorial, the second derivative of B of j omega evaluated at omega equals 0, multiplied by omega squared, and so on, right? So that's what I will need. Now the strategy is, in order to force absolute of B of j omega, this guy, to approximate h of j omega, the ideal filter. If I want this to become, the green to become black, I'm going to pick the undetermined coefficients in B of S, A0, A1, B0, B1, B2, B3, so that as many derivatives of cap B of j omega are equal to 0 as possible. I ideally want all these guys to disappear. This guy to disappear. That's the linear term. That's the quadratic term. I want all of them to disappear. Why? Because I want the behavior at low frequencies to be maximally flat. If it is maximally flat, that means I only need a contribution from a constant term like this, B of j0. That's it. I want this to be flat. No linear term, no quadratic term, like no other term. I want all those derivatives to go to 0. I only want a flat behavior at 0 there, right? So let's take a look. How do you do that? So this is the goal. The goal is, let me highlight this, as many derivatives of B of omega equal to 0 as possible. So all the pink terms should go to 0. If they go to 0, I may get some constants, A0, A1, B0, B1, B2, B3, that make that happen. That's what I'm after. Now, coming to the next slide, which is to consider absolute of B of j omega whole squared, right? You are considering the square of the frequency response, square of the magnitude of the frequency response. Why are you doing that? Because if we don't do that, we are differentiating B of j omega, which means I will have a lot of j's to worry about as I'm differentiating with respect to omega. And that might make my analysis very, very complicated. So in order to keep things, relatively speaking, a little bit easier, I'm going to consider b of j omega multiplied by b complex conjugate of j omega. So if I do that, notice what happens. B of j omega is simply b of, what is this term? B of j omega. How do I get that? I will evaluate the transfer function at s equals j omega. How do I get this guy? B complex conjugate of j omega. I will evaluate b of minus s at that same point, s equals j omega. So I will take the generalized transfer function b of s from before. I will plug in j omega for s, and I get that. And I will do that for minus s, and I will get that for the blue term there. Once I do that, I will multiply, and because these are complex conjugates, the j terms will cancel out. And what you will be left with is a new new frequency response, which is now the magnitude squared of b of j omega, but no j terms. But instead of finding a0, a1, b0, b1, b2, b3, now our goal will be to find d0, d0, d2, c0, c1, c2, c4, c6 instead, right? Some other coefficients. But because we no longer have j terms here, the derivatives with respect to omega are going to be much easier to handle. So instead of looking at Taylor's expansion of b of j omega, we are now looking at Taylor's expansion of magnitude squared of b of j omega instead. So expanding absolute squared of b of j omega using the Taylor series, we have a similar result here. Function evaluated at 0, omega squared. Function evaluated at 0, omega power 4. What are we doing here? We are using omega squared as our x, right? So earlier we had constant x squared, and so on. But now because we have only terms such as omega squared, omega 4, omega 6, we are expanding that in terms of even powers of omega. But we are still evaluating those functions at omega equals 0. So if you do this for that function, and if you can trust me for now, what you will have is a constant term d0 divided by c sub 0. Those are from here. The omega squared term will be this, omega power 4 terms will be this, and then so on. Now what do we want? We said we want a maximally flat behavior, which means that we only want a constant. All the derivatives should go to 0. So if we only want a constant, actually just 1, right? Like we want that gain to be 1. We want d0 to equal c0, right? We want that to be a 1 there. Actually, I was using green, I think. That will give you that. And all the other terms should go to 0. So if I want all of the other terms to go to 0, I want this guy to go to 0 here. So if I'm able to use d0 divided by c0 as 1, and that has to go to 0, that means that d2 should equal c2. So that will give me that. And similarly, if I apply that to the next term, I get c4 to be equal to 0, because this is already 0. So the other term will go to 0 if c4 goes to 0. Now using this, so far the approximation has become magnitude squared of b of j omega is, now we have used d0 equals c0. After using these three conditions, we can write that out in terms of c6, c0, and c2. Only three coefficients to determine now. 1 minus c6 omega 6 divided by c0 plus c2 omega squared plus c6 omega power 6. So we are still down to three coefficients that we need to find out in order to get a Butterworth filter as close to an ideal filter as possible. So let's keep on with this exercise. Here we are going to use our second condition. The second condition is, as omega goes to infinity, our magnitude squared of b of j omega should smoothly go to 0. So we are again going to use Taylor series, but we are going to expand it at omega tends to infinity. So instead of evaluating that at omega equals 0, we will evaluate that as omega equals infinity, at infinity. In other words, if we can define another variable v, which is the reciprocal of omega, then we can expand magnitude squared of b of j 1 over v about v equals 0. So it's the same thing as saying expand this guy with respect to that is the same thing as saying expand this guy with respect to that. So once we do that, we have substituted 1 over v instead of omega in the previous approximation, simplified it, applied the Taylor series expansion, constant term, first derivative, evaluated at v equals 0, v squared, second derivative, and so on. Now, what do we want? We want this to go to 0 as v goes to 0. We already got two zeros here. Our third term was c2 divided by c6 v raised to 4. We want that to go to 0. One way of making that, the only way to make that happen is c2 should equal 0. We got our another coefficient. Plug it in this. What do we have? Absolute magnitude squared of b of j omega is c0 divided by c0 plus c6 omega raised to 6. Rearrange that to write it in a very nice manner, which is 1 divided by 1 plus omega divided by omega c. We are defining cutoff frequency omega c to be c0 divided by c6. Let that be the cutoff frequency. And there is a reason for that. Anybody say why we are defining that as c0 divided by c6? What is cutoff frequency? How is it defined? And those two answers will tell you that. The cutoff frequency is where the magnitude squared of the filter should become half power bandwidth, right? Like that should become half. And the only way this can become half is when omega divided by omega c equals 1. So the frequency at which that happens is omega c. So clearly our assumption, our definition, or I should say letting c6 divided by c0 to be 1 over omega c sub power 6 makes sense because of that. All right. So here is an important result here for Butterworth filters. 1 divided by 1 plus omega, your frequency variable, divided by a constant, which is actually your cutoff frequency of the low pass filter, raised to 6. That is the magnitude squared of b of j omega. Now, there is a relationship. We started off with a third order filter. I want you to note something. If you started off with a third order filter and you ended up with a power of 6, twice that value, you will see that there is a pattern with this as you go forward. So now coming to the poles of the transfer function, because we were after how should I design this Butterworth filter. So let's talk about where the poles of this transfer function are. We are still after b of s. We arrived at square of that, right? So we still need to go back. So let's see. Write absolute of b of j omega squared in terms of b of s. What do I need to do for that? We simply need to write that in terms of s and evaluate s as j omega. That's essentially what b of j omega will be, squared will be. When I do that, I get 1 divided by 1 plus omega divided by omega sub c raised to 6, which implies I wrote b of j omega absolute squared as b of s multiplied by b of minus s. That is the same as this. That's how I started this derivation. So they should be equal. This should be equal to this in terms of s. Omega c is a constant, cutoff frequency of the desired low pass filter, raised to 6. Third order, you get 2 times the third order there. So where are the poles of b of s multiplied by b of minus s? The denominator should go to 0, right? That means the 1 plus s divided by j omega c should go to 0. That's going to give you the values of s for which this happens is going to give you the poles of the Butterworth filter, the third order Butterworth filter. So let's do that. Find s that makes this happen. Rearrange s divided by j omega c raised to 6 equals -1. -1 can be written as e raised to j pi multiplied by an odd multiple. So as k goes from 0, 1, 2, 3, 4, 5, you get an odd multiple of pi here. Cosine j pi 2k plus 1 plus j sine pi 2k plus 1 is going to evaluate to minus 1. Why only 6 terms here? There are only 6 terms here. Why? Because there's power 6, right? So there are only going to be 6 poles. Continue with our discussion. Rearrange. So I need s. I got to s divided by j omega c raised to 6. So I can write s by first making the right side, taking the 6th root of the right side, which will give me e raised to j pi over 6 times 2k plus 1. I have still a j omega c left over here, which can go into the numerator on the right side. So s, the values of s, or the poles of this third order Butterworth filter, are in the s plane at j omega c e to the j, all of that. J is what? J can be written as e raised to j pi over 2. So combine the two complex exponentials to write a convenient form. The values of s for which I get the poles, or the denominator goes to 0, is actually omega sub c. That's the magnitude, right? That's the magnitude. That's the distance away from 0. And there is a phase to it. E raised to j times pi over 2 plus pi over 6 times 2k plus 1. So as k goes from 0, 1, 2, 3, 4, 5, there are going to be 6 of them because the denominator is of the order 6. I will get 6 different angles at omega c away. So if I sketch it on the s-plane, and you can quickly evaluate that, put that into a table, k equals 0 through 5, evaluate the angles that are present in the exponent here. Yellow, all of that is yellow, and that's what is here. You will see that in the s-plane, you will get 6 poles for the 6 roots of the denominator. Each one for k equals 0, 1, 2, 3, 4, and 5. They will all be on a circle of radius omega sub c, because that magnitude is omega sub c. Whatever cutoff frequency you need for the low pass filter. But they will have a different angle. What are those angles? Pi over 2 plus pi over 6, 90 degrees plus 30 degrees, 120 degrees, right here, k equals 0. You got that. And they're all going to be separated equally. So pi over 3 degrees apart, 60 degrees apart. So you get 120, 180, and so on. All 6 of them. Now it turns out 3 of them are on the left half plane, good, stable. 3 of them are to the right half plane, unstable, bad, red. Right? So half of them are green, half of them are in the red zone. So we were after b of s. We got b of s multiplied by b of minus s. So we can throw away all the 3 poles on the right side, and that is going to give us our transfer function for a stable third order Butterworth filter when k equals 0, 1, and 2. That's how you go there. So filter must be stable. So we are going to pick the left half plane for the poles represented by b of s. B of s consists of 3 poles. Where are they? They are all omega c away from origin at angles 120, 180, and 180 plus 60. So the pole 0 plot, instead of having 6 poles, now it is down to 3 poles. They're all omega c away from origin. This is the real part of s. That's the imaginary part of s, or sigma and j omega. We write that. The poles marked by crosses are omega c distance away from origin, and clearly because of the angles that we have derived for this angle will come out to be 60 degrees. So which means that you can say the height over here is going to be omega sub c sine 30, so square root 3 omega c divided by 2, and then the distance over here is going to be omega sub c cosine 60, or half of omega c, right? Just trigonometry over here to pick out where the poles are. So for example, pole at 0, k equals 0 and k equals 2 have a real part of negative omega sub c divided by 2, and the y of them is plus or minus square root 3 omega c divided by 2. So those will give you 3 poles. One for k equals 0, one for k equals 1, one for k equals 2. So now we know in order to have a stable Butterworth filter, where should your poles be? They should all be on the left hand side, those corresponding to k equals 0, 1 and 2. And we have evaluated that. So you're given a cutoff frequency for the low pass filter, you can put those poles there, evaluate, and you have got the transfer function right away. But you need to still do a little bit of manipulation, and I'll talk about those. Once you have these locations, location 1 for the pole, location 2 for the pole, location 3 for the pole, then because we know that those are poles, they all go in the denominator. So you can write down their corresponding factors in the denominator right away. However, we also know that in the pass band at frequency 0, we want B of S to become 1, gain 1 filter. So we are going to manipulate B of S numerator to omega sub 3 so that at frequency 0, the magnitude of B of S becomes a 1. So omega sub c is the cutoff frequency. It's a value. It's a constant. So multiplying by that in order to get a gain 1 filter, it should not make any difference. So the final transfer function for the third order Butterworth filter will look, so if you simplify this a little bit further, you get omega sub c cubed, the numerator remains as is, the denominator becomes s cubed plus 2 omega c s squared plus 2 omega c cubed s plus omega c cubed. That is the final transfer function of a third order Butterworth filter. It's also in the text with that particular equation. Now you can use MATLAB to kind of do some fun activities with this. So if you have, we have the B of S that we derived earlier. If we make the cutoff frequency 1, you can sketch the magnitude of the frequency response of the third order Butterworth filter using these commands here. So first n equals 3, that sets the order of the filter. Then you have 3 variables for z, p and k, for zeros, poles, and the gain constant k. You use the BUTTAP, that's the function for the Butterworth filter of order n. That will help you give the location of the zeros, there are no zeros there, the location of the poles, and the gain constant k. Using those and there's a body plot command that you can use to sketch out the magnitude and phase of the third order Butterworth filter as well. So this piece of code is available to you if you want to play around with the higher order Butterworth filters and see how the magnitude of this filter changes as you increase the order. Obviously that needs to become more and more sharp. Okay, so let me take a look at the time here. Okay, so I still have a few things that are left over with the general Butterworth filter discussion. So I'm going to try to make a video for you guys to watch offline, and I will make that available. So let me stop the recording here and discuss a few things with you guys.